All right, guys. Thanks for coming to the talk. I've got maybe like I lost my microphone. I've got maybe like an hour and a half long talk I was going to give on DataFrames. A little bit of background myself. I work as a trainer at Databricks. I've been there for about 1 year now, and I've taught like maybe 20 classes on Spark. Before joining Databricks, I did freelance consulting and training on big data. I taught a whole bunch of classes on Hadoop and Cassandra and NoSQL architectures in general. I wanted to mention something. If you are interested in taking a 3-day Spark class, then you just have to Google these 3 terms, and then this is a code that will give you 15% off. I think it's in about 2 more weeks in San Francisco, kind of close to the Embarcadero, is where we're planning on running this class. Most likely, I will be one of the co-instructors there, along with probably another instructor who will be teaching most of the class. So anyway, if you want to go deeper into Spark, this is a rare opportunity. We usually don't do public classes in the Bay Area. We're just pretty swamped with a lot of private classes right now. Okay, so this entire slide deck, by the way, will be online eventually. Since I just finished it right now, a few minutes ago, I wasn't able to upload it yet. But when I get back home, I will upload it. I'll add a comment on the meetup page to a SlideShare link where you can get this. It might be sometime tomorrow morning before it will actually be up. Okay, I want to understand a little bit about how technical you guys are as far as in your Spark knowledge goes. How many people here have used Spark hands-on? Like you actually did some transformations or actions? Okay. Next, how many people here have used DataFrames in any language, whether it's R, Spark, Python? Okay, a few people. Let me ask a couple more slightly more complicated questions. How many people here know what like a narrow versus a wide dependency is and would be able to explain the implications of the two? Okay, that's fine. So let me talk about what I'll be covering. Basically, what I want you to get is be able to smartly use DataFrames tomorrow. So I kind of calibrated this talk to have some intro level stuff, some advanced level stuff, and a little bit of hands-on demo as well. All right, so if you've been doing Spark for a year, I hope you'll still get something out of this. And if you're completely new to Spark, same thing. I hope you'll still get a lot out of it. Okay, so Databricks is the company that is one of the primary contributors to Spark. In the last year, Databricks committed about 75% of the source code to Spark. This is basically the architecture of Spark. So at the very bottom, we have what has been big data for the last 5 years. It's all the NoSQL stuff and some relational databases as well. So Spark essentially can connect to any of these data sources through the Spark Core API. And right above that is the RDD API. And this has classically been the way developers use Spark. They learn how to make a base RDD, they transform it to a bunch of different RDDs, then they eventually call an action on it to look at the results in the last RDD. In the last couple of years, though, DataFrames, well, in the last couple of years, we've gotten a bunch of higher-level libraries for Spark. And now there is a new DataFrames API. And I put DataFrames way at the top, closer to the actual programming languages, because this should be your primary interaction with Spark. For the past 2 years, or the past 3 or 4 years, it was primarily RDDs. But we're kind of like at a line right now in the evolution of Spark. And you're literally sitting on that line right now. If this was a talk like a year from now, it would have been almost exclusively on DataFrames. And when you get into something that you cannot do with DataFrames, like you want to do image recognition, facial feature extraction, or work with unstructured data like blobs of text, that kind of stuff doesn't fit well into columnar type of data sets. So then you will need to use RDDs. The RDD API is not going away. So the goal of Spark is to give you a unified engine across many data sources, workloads, and environments. There are many different production level implementations of Spark. Here are some of them. And Spark has a really massive user community. If you look at the number of commits per year, it kind of supersedes most of the other big data projects. The number of contributors per month to Spark is also on a meteoric rise. So this is still kind of old. This is kind of, I think I took this snapshot at the beginning of 2015. It is essentially the most active project in all of big data, and it's the most active project under any functional programming language. So as you know, Spark is written in Scala. So I'll just kind of fly through some of these intro slides. There's about 700 contributors right now, about 450,000 lines of code right now. And we actually don't know how many production deployments there are because most people don't talk about it publicly. But we know about 500 to 1,000 production deployments right now. And there's a lot of large-scale users of Spark as well. Tungsten is running a big Yarn cluster, and in that Yarn cluster, they're running multiple Spark applications. So this is the largest one we know about. It's about 8,000 physical nodes in the Yarn cluster. The largest single job, Alibaba is running a production 1 petabyte Spark job. And at Databricks, around this time last year, we did a benchmark doing large-scale analysis on 1 petabyte of data as well. You might have heard of the 100 terabyte sort. This is kind of what we did right after the 100 terabyte sort. There is a neuroscientist on the East Coast who is connecting zebrafish brain to some sort of like imaging technology, and he's then the images are being fed into Spark streaming at the rate of 1 terabyte per hour, and this is the largest Spark streaming job that we currently know about. And there's also a 100 terabyte sort record. This is the sort record. In 2013, Hadoop won the sort record. This is the team at Yahoo who competed using 2,100 machines in a physical data center. It took them about 72 minutes, and that is pretty impressive for going through 100 terabytes. Each record is 100 bytes. The key is randomly generated. Using an algorithm that they give you in the competitions. The key is 10 bytes. The value is 90 bytes, also randomly generated. All right, so there's about 1 trillion records here. All right, so Spark did this last year. This was a team at Databricks that used 207 machines. This is the first time the competition was won in the public cloud. We did this in Amazon, and it occurred in about 23 minutes. Okay, so for people who are new to Spark, I'm going to fly through the next 4 or 5 slides just so I don't lose you in the terminology when I go a little bit deeper into DataFrames. So at the core, the Spark application is essentially a driver JVM. This is like where you write code. This is where your REPL is, like your PySpark REPL or your Scala REPL, and you type code into the REPL. So this usually sits on your laptop, and that connects to 1 or more executor JVMs, which is where the actual tasks run for your Spark job. The executor JVMs are roughly between 10 to 40 gigabytes heap. This is like maybe 2 to 10 gigabytes heap. Right? So this is just a Spark application. And if you're completely new to Spark, you might need to know one more thing, that traditionally the data set for Spark has been an RDD, a resilient distributed data set. Here we have a RDD with 4 partitions. You can see there's basically 3 log line messages in each partition, and I'm going to name this RDD the log lines RDD. So how does this actually scale? Imagine here's an RDD with 5 partitions, 1, 2, 3, 4, 5 partitions with 2 items in each partition. So the trick is, the more partitions you have, the more parallelism you have. Here we have a 3-node cluster with 3 executor JVMs. And the way this essentially works is maybe the first partition will live on this executor in its heap. And maybe the second partition will live here, third one there, fourth one there, and fifth one there, right? So this is basically how you scale a RDD across multiple nodes. If this RDD had only 2 partitions, and then you did something with it, like some compute, you would not be using all of your cluster. So if you want to really use all of your hardware, try to have as many partitions as you have the number of machines. Usually, though, you want to actually look at the number of slots you have in each executor, meaning how many tasks can you run in each executor. If it's 10 tasks max, 10 tasks, and 10 tasks, then that's 30 tasks. And if you really want to use all your hardware, you should have an RDD with 30 partitions. If you have an RDD with 60 partitions, then you'll compute the first 30. That's the first wave of computation. Then you'll do the next 30 on those same slots. All right, so it's perfectly normal to have like 20,000 partitions, but not nearly as many slots on the executors. Okay, so how does this new thing, this DataFrames API work? It is a concept that lives across all programming languages. So it's a really powerful construct. If you learn how to use DataFrames in Scala, then you can very immediately be productive in Java, Python, and R as well. So here's how the data model now looks a little bit different with DataFrames. So here we have a data frame with 4 partitions. But now there's some extra stuff going on. So the data frame size itself is 4 partitions. But notice that under each partition, what we've done now is for every column, we've named the column and we've typed the column. So the name of the column here is first type of error message. And then that is of type string. Then there's a timestamp of type integer, and then there's the actual error warning or info message, which is also of type string. So this is kind of very similar to the original RDD that we saw, but notice here that each record was actually a line. So we have 3 records here, and the commas are still in there from the original data source, the actual file that you read. But when you actually get an RDD, even if you get it from a CSV file, it will find those delimiters like the comma. It will get rid of them, and it will actually orient the data in a columnar format. So one of the cool things that DataFrames can do is when you cache this in memory, a data frame can actually optimally compress this column because it knows it's of type string, versus this is a column of type int. All right, so you get this massive performance optimization as far as how much this same data will take when it lives in the heap of the executor. Another interesting thing you can do is you can figure out things like statistics. Like imagine that you're only looking for rows or messages where the time is less than 7 days ago, and you actually have stuff from the last year here. So DataFrames can look at statistics on each partition and figure out that a partition, an actual column that is of type int, actually does not meet the criteria of the last 7 days. And then it will not even look at this partition for computation at all. Right, so this is like another internal trick that DataFrames can use. If you're using RDDs, you still have timestamps, but when you use the RDD API, these objects are they're opaque. Spark can't tell that this timestamp, all of these timestamps are actually not from the last 7 days. It has to actually process each one of them. Right? So this is an extra trick that DataFrames gets you. Okay. So this is the DataFrame model. It's still similar. It's made of partitions, and each partition will live on a different executor. All right, the main thing so far is there's a type on the column and there's a name on the column. And that gives a lot of interesting internal optimizations. So DataFrames are easier to program, as you'll see in a second, and it will give you much better performance and much better storage in the heap of the executor. All right, so I'm going to spend more time talking about the performance later. I want to kind of talk more about programming RDDs and do a quick demo, and then I'll actually talk about how the internal optimization happens. All right, so final review slide. Here we're trying to compute an average. If you do that in Java, MapReduce, it takes many lines of code. I'm not going to bore you with this. If you use Spark RDD API, it uses much fewer lines of code. This is the RDD API code from right there. But it's still really weird to figure out what's going on. If you use DataFrames, the exact same computation can be done significantly faster. So all we're doing here is looking at a people table, grouping the people by name, and then we are trying to find the average age for each name, and then we're collecting that information back to the driver. Much easier to understand, and the cool thing about DataFrames is that this same code, as you run it on newer versions of Spark, it will be optimized using new rules that are being created for Catalyst. So the same thing will just be giving you better performance as you upgrade Spark. Versus if you write using RDDs, you're basically stuck on, well, there might still be some optimizations that will happen, but not nearly as many. Yes?
So, I mean, I know DataFrames, I've used them without and all. It seems like this DataFrame would be the data interface at the beginning, right? If I have a huge text file which I need to work with, but more importantly, I need to continue to use the RDD paradigm to actually use the data which I get in, and then further make vectors out of it and massage it and do stuff with it. So it will let me do that, right?
That's perfectly normal. You can, I actually have an example of this in the demo. You can create your original, from the original data source, you can first create an RDD if that's what you like, and maybe you have some previous code you already wrote to get the RDD transformed into the actual way you like it. And then you can actually take that RDD, and then as long as it's a structured set of data in the RDD, meaning it looks like comma delimited or tab delimited, then you can convert that RDD to a data frame and then work on it in this much nicer API, and then you can drop down to RDDs whenever you want. So you can go back down to that layer, and then you can finally go back to DataFrames, then save it in a nice, clear, easy to understand way. So you can move back and forth. Now, not all of the RDD API is exposed to DataFrames. So it's a subset. There are certain things that are not exposed. Another thing you can do is actually on the data frame, you can make a UDF to do things that the DataFrame API doesn't let you do out of the box. So I have examples on that as well. OK, so one last thing before we go deeper into, I'll hold, unless it's a critical question just for applied to the slide, I'll leave some time for Q&A at the end. I want to kind of fly through a bunch of material, or else I might get bogged down. Last thing you should know about DataFrames is that they are, just like RDDs, they're lazily evaluated. So if here we have a original DataFrame 1, we transform it to DataFrame 2, transform it to get DataFrame 3, and then we call an action either to take the results of this DataFrame back to the driver or to a notebook that you're working on, or you can take the DataFrame and write it down to distributed storage. So that's essentially what an action will do. It will cause this last DataFrame to either be sent to you for evaluation or write it down. Now, the way this actually works is when you call an action, then Spark will actually materialize all of these data frames, and sometimes it'll do interesting optimizations here as well. OK, so this is actually the evaluation phase. When you so that I got rid of the dashed lines and there's solid lines, because once you actually call an action, it's actually evaluating them. OK, so here are some transformations that don't cause the data frame to be computed. So all of these are lazy. If you make your original data frame and you do any of these things, it's not going to actually do any computational work until you call an action, like one of these, to actually see results. And then Spark will, as you'll see later in the demo, it's going to do all sorts of things to try to optimize these to run as few tasks as possible. All right? You might be familiar with this concept if you know about pipelining in RDDs. OK. So another interesting trick with data frames is actually everything that a data frame does can be expressed with one of these three transformations in the RDD API. So if you've been using the RDD API, you probably know there's something like 60 or 70 transformations, and there's like, I think, 25 or 35 actions, right? A lot of those transformations are actually just calling each other. And they're kind of utility functions to make it easier. But to take an even further step back, everything in data frames is either a map partitions transformation, a zip partitions transformation, or a shuffle. Right? So these are the three like fundamental transformations actually in even the RDD API. OK. So Spark SQL, it came into Spark around April 2014 in Spark 1.0. It graduated from alpha in 1.3. and there's a lot of work being done in it right now. It's one of the most actively worked on projects within the Spark ecosystem, and you can see the number of commits and number of contributors increasing quite a bit. Okay, so if you're new to DataFrames, when you start looking at DataFrames, you'll see that you have to first take the Spark context, and from that you have to get either a SQL context or a Hive context, and then you can actually start making your DataFrames. All right, so in general, what you should know is always use the Hive context, unless there's a really strong reason you might not be using it. But it doesn't matter. It doesn't matter if you're using Hive or not using Hive. You still want to use the Hive context. First of all, it uses the Hive QL parser, which is a much richer parser than the basic functionality you get in the SQL context. And also, the Hive context lets you read from the Hive metastore and Hive tables, and it gives you full access to the community's Hive UDFs. So this is not the default in Spark, just because there's a lot of dependencies that would have been added to the Spark source code to make this the default context. But in production or even for prototyping, I highly recommend using this all the time. OK, and also you should know that Spark SQL is actually the only project I'm aware of that supports multiple versions of Spark. So I think the Spark 1.5 code base that's coming out in the next couple of weeks supports everything from Hive 0.12 up until Hive 1.2, I believe. So almost like the full spread of production Hive installs. OK, so how do you make a data frame? On either the SQL context or the Hive context, you can read a table from Hive really simply. All you need to do is actually take the Hive site.xml file and drop it into your Spark configuration folder. And then you start Spark up, and then basically you can just access all of the Hive metadata. All right, very simple. Here we're making a data frame out of a S3 path where there is a JSON file. Here we're reading some Parquet data using Scala. And here is the Java implementation for reading Parquet data. All right, very simple, one line of code. You get a data frame. And then when you have a data frame, what do you do with it? If you have a user's data frame, you can filter it to get everyone who's under 21. You get the young data frame. Or you can use Panda syntax to do the same thing. You can increment everyone's age by 1. Count the number of young users by gender. It's very readable code, is my point. As opposed to using the RDD API, this is very user-friendly code. Another thing you can do with data frames is you can register your data frame as a temporary table. Here I'm calling it young, the young table. I'm registering it here. And then finally, you can start using the young table for SQL queries as well. So you can kind of move back and forth between the DataFrames API and the SQL API. OK, so that is basically all the intro stuff. I have a bunch of other stuff I wanted to cover that kind of goes a little bit more behind the scenes. So to conclude this section, I wanted to mention here are some of the actions on DataFrames. So remember, these are the things that are going to actually cause the entire data frame DAG to actually be computed. All right, so you can collect the results of a data frame back to the driver or your notebook. You can count how many items are in a data frame across all the executors. You can get just the first row. Show gives you the top 20 rows. Here are some functions on data frames. You can cache a data frame, return all the columns, return all the column names and their data types. So it's like almost like the schema of the data frame. You can do explain. You can persist a data frame to memory. You can unpersist it. You can register a data frame as a temp table before you call SQL on it. And you can print the schema of a data frame. OK, here's a few more functions on data frames. You can unpersist a data frame out of memory if you don't want to cache it anymore. OK. Queries on data frames. You can aggregate columns on data frames. This shows you the rest of the operations. You can take a data frame and you can write it back down to JSON, Parquet, JDBC, Cassandra. It's basically a really simple method. There's write, and then you can pass in the exact data store that you want to write to. Much simpler than working with RDDs. And then finally, there's many operations on data frames. And I won't cover all of these, but you can see there's you can kind of skim through some of these. I'll cover a few of these in the demo. OK. Let's start going into some of the little bit more behind-the-scenes stuff. So you can create a data frame from many data sources, Hive, or you can take an existing RDD and you can get a data frame out of it. So the data sources API is one of the most important things you should start looking at before you look at data frames. This provides a mechanism to read structured data from many different places. Here are the built-in sources that are supported right out of the box. And then you have to usually go to Spark packages and download some extra library to get to some of the external sources. OK, so this is the Spark packages website. These are the data sources that you can get on the Spark packages website. I found a mainframe connector, which is kind of funny. That kind of popped in there in the last couple of months. OK, so this is just showing you how to read from JDBC. This is new in Spark 1.3. We're basically reading from Postgres, this table, and we're calling the table impressions, and we're then just running SQL on it. All right? So the JDBC connector supports almost any relational database, anything that's JDBC or ODBC compliant. So how is this different from just making an RDD out of a JDBC connector? Well, one of the cool things you get with the DataFrame API is it supports predicate pushdown. What that means is if you only care about certain columns in the relational database, then you won't have to read all of them in and then filter them in Spark. Spark DataFrames will actually tell the relational database to prune out certain columns and only give certain data back. So it has less data to work with in the Spark layer. OK, another cool thing you can get with the JDBC server is that many users can send SQL queries to the same JDBC server. So the same one Spark application can actually be shared between many end users. OK, so I mentioned the fact that when you use data sources, some input data sources will actually let you skip through the I/O read. So I want to kind of mention this a little bit more. OK, so how does Spark actually let you read less data? One thing is it uses partitioning. So if you're using Hive partitioning or Parquet partitioning, and I have a slide on Parquet partitioning, then what it will do is it will let you just completely skip certain directories. Right? This is like a massive speed increase. And another thing that I already mentioned is using statistics. So once you have a partition, Spark can decide to look at statistics in that partition to just maybe skip that partition completely. All right, there's another major benefit with DataFrames. Let's look at Parquet. So Parquet should be your go-to source for reading data into Spark SQL. We probably see more than 50% of end users actually using Parquet. So if you have your data in JSON or comma-separated value files, I would highly recommend making your first data frame job be an ETL job to convert that down to Parquet so that then you're always operating on Parquet. So I think that Parquet deserves a few slides to talk a little bit more about. So this is a project that was made jointly by Cloudera and Twitter around the fall of 2012. It entered the Apache Incubator around May 2014. And I think they're at like version 2.0 right now. So one of the most important things to understand about Parquet is that it is a columnar oriented format. If this is the way you think about your table, it has 3 columns, 5 rows. Then if you use a row-oriented layout, the way this would actually be stored is you would store the entire first row, then the second row, and then the third row. And that basically gets appended to the end of a file. And that's your database file. If you use a columnar layout, what Parquet does, for instance, is it'll take the first column and store that in a file, and take the second column and store that in a file, and take the third column and store that essentially like in a file. So what this lets you do is if you have, at the simplest terms, if you have 3 different files, but if your SQL query only cares about 2 of them, then you never read that third file. Plus, you can optimize the compression of this much more efficiently. OK, so how does the actual Parquet file format look? So here we have an actual file format. Remember what it's doing here is essentially Parquet is going to take a few rows, maybe all of these rows, and all of these are going to be called a row group. Within the row group, you can see there's actually multiple columns. There's actually 3 columns, so we need to store them separately. OK, so here's our row group. Inside the row group, there's a column A, column B, and maybe column C. All right. And at the very end of your Parquet file will be a footer. And the footer just basically has basically 2 things. It has a whole bunch of metadata, like the schema and the version of the Parquet file. And then for that row group, right, for the row group 0, it has all of these things, like the type, encodings, num values, the offset of where the row group starts, and then metadata for each one of the columns, like column A metadata is what we were looking at, column B metadata, and so on and so forth. So why is this stuff important? Well, the main reason I wanted to point this out is because when you are reading Parquet, Spark has to auto-discover the data format. So Spark is going to read this entire footer. It's going to use a separate Spark job to do this. And I'm going to demonstrate this in just a little bit, because there's this interesting implication here. So there's 2 things Spark will have to do to actually use this Parquet data. The first job is going to have to read the footer to understand the layout of the data. Then the second Spark job will actually start reading the columns that you actually care about for that specific Spark job. All right, so this is what this is saying. We have to first auto-discover the data that has been partitioned into folders. And then finally, there's another Parquet feature called metadata merging. What this is saying is that if you add or remove columns in your data file, Spark can automatically scan this footer file to understand how the data has changed. So you don't have to tell Spark anything new about your new format. And finally, this was something I kind of touched upon earlier. In Parquet, what you can do is you can store data like in different subfolders. These are called partitions. So this is partition 2014, partition 2015, and then you have your Parquet data under each one of these partition folders. And the cool thing here is that Spark can only look at the folders that have the data that you care about. OK, so finally, here's basically a ETL job like the one I mentioned. Maybe you want to read some JSON data. You're not reading all of it. You're kind of sampling maybe 10% of your JSON data. And then you're loading it into a data frame called DF. And then all we're doing on this data frame is writing it back out immediately as Parquet. And we're partitioning it by year. And we're also saving it as a table as well. So instead of save as table, what you could do is save it to some other source, like Parquet, like an actual Parquet format in S3. Right, but this is actually a fully functioning ETL application. Doing this in even RDDs takes way, way longer. OK, so these are the actual actions that are causing the data to be read or to be written out. OK, so one interesting thing I wanted to talk about is statistics. Statistics are logged when you cache a data frame in memory. So imagine that what we're trying to do here is maybe we're trying to read all of the data where a specific column is 8 or above. So our predicate is basically we're looking for A equals 8. Right? So notice here that in this partition, the A column doesn't have an 8 at all. So what Spark does is if you cache this data frame in memory, when it does that cache, it's also going to compute statistics on each one of the columns in the actual partition. And in those statistics, it keeps track of the max number, the min number, an average, and a bunch of things like that. So for example, here, it knows that the max for A is 9, the max for A is 7, and the max for A is 8. So here, on these two, for example, there's a chance that A equals 8 is in there. So we'll actually look at these two partitions. And it'll completely skip this partition in memory. So this was kind of the same thing I kind of mentioned, but in a little bit more detail. And you can kind of go look at these two JIRAs to get more information on how this actually works, the implementation of it. Right, this is something that would not have been done if you're using RDDs. OK, another trick I wanted to mention for like kind of behind the scenes kind of optimizations. with data frames is that if you have a data frame, and then imagine you do some sort of shuffle operation and you get another data frame out. So what happens in Spark right now, in Spark 1.4, the number of partitions that will come out in the new data frame after a shuffle is static and it's fixed. So that setting is called Spark SQL Shuffle Partitions. And I believe it defaults to 200. You can change it like this. On Spark, on the SQL context, you can set conf, and the key would be this, and the value would be 200, and then you can change it. This is a static setting. Why do I mention this? Well, I mention this because every time a shuffle happens, now your next data frame will have 200 partitions. This might be a good thing. It might not be a good thing. You might want to control this in a more manual way to really scale across your cluster. Or maybe 200 is too much for you. You actually want to limit it down to just 2 partitions or 5 partitions, right? I just wanted to make you aware that right now this is a static setting, but in Spark 1.6, a new adaptive shuffle is going to be released. What this is going to do is when the map spill data gets written out from before the shuffle, then Spark will actually look at the data in the map spill files, and based on that data, it will try to optimally decide how many reducers to start to create the partitions in the downstream RDD. So this is still being developed, but maybe in about 3 or 4 months this will exist. OK. And another thing about caching an RDD, caching a data frame, if you cache it, I mentioned a few benefits for it already. Another benefit I wanted to mention is that Spark SQL will re-encode the data into byte buffers before calling the cache, so there's less pressure on GC. So this is essentially kind of like even better than serialized objects in memory. OK, now I'm going to do a demo, and I want to kind of get you guys to actually see a few cool things about data frames. And then after this, I had like maybe a 10 or 15-minute talk where I was going to talk a little bit more about the Catalyst optimizer. And after you kind of see how you work with data frames, I wanted to kind of show a little bit about what happens under the covers in data frames. I thought this would be kind of cool for people who had already been using data frames for a while. OK, so to do my demo, I have a Databricks notebook. So if you haven't used Databricks, this is essentially a notebook that lets you write Spark code and launch clusters. So I launched a cluster here in the Amazon cloud, this one, the 7 p.m. 24/7 demo. There are actually 8 worker machines and 1 Spark master here, right? So I'm going to go ahead and open up this UI. And I want you to see that there are no Spark jobs that I've run so far. So this is kind of like a fresh cluster. And we're going to do a few things and kind of look at how those things execute as jobs. So the next thing I need to do is I'm going to open up a notebook. So let's create a Scala notebook. I'm going to call this 24/7 demo. And I'm going to attach this to my 7 p.m. cluster. All right. So the first thing I'm going to do is just import some implicits. You can ignore this. And next, there's this file here. It's in Databricks file system, which is just a wrapper around Amazon S3. So I have this JSON file, people.json. I'm just doing like a ls on it to show you that this is just one file, and that's like the size of the file. It's a relatively small file. So next, I'm going to actually read this. I'm going to read this into a data frame. And then I'm going to ask kind of a trick question and see if somebody can figure it out. So let's make my first data frame. So all I have to do is run SQL context and read JSON. And then I'm just going to give it the path for Databricks file system. And I should now have this first DF. It looks like it actually figured out a bunch of things about the structure. So my first question for you guys is this, especially people who have been using RDDs, If I go back to my UI now, will a job have executed, yes or no?
No.
How many people think it would have? No one. How many people think it would not have executed a job? Most people said no. You're kind of not raising your hand, but I heard a lot of no's. But I want to point something out. It looks like it did actually run a job. Ignore the two displays. Those are just us looking at the file system. This is actually the job that ran, and I'll prove that. Look, there's 3 jobs right now. Let me run that one more time, and I should have a 4th job. So this is going to be new if you're coming from the RDD API. Oh, I didn't do any ETL yet. I haven't done anything with the data frame yet, actually.
No, you've read the metadata, though, right?
That is exactly true. So let's kind of go a little bit deeper.
5 minutes ago.
So first of all, I want you to see that this job had 1 stage and it needed 2 tasks, and both of them completed. So 1 stage, 2 tasks. Let me go inside this. This is kind of a cool thing in Spark. You can click DAG visualization, and I can see what's going on inside my stage. It seems to have read an RDD, then it did a map partitions, and a tree aggregate. These are all just things it did internally. But I want to ignore all of that right now. I want you to see that this needed 2 tasks. It read about 13 megabytes of data. So if I come here, and if I do this, I want to convert the bytes to megabytes. How much data is in this file? It's 13 megabytes of data. OK, that's my JSON. Then if I come here, it looks like my input was also showing up as 13 megabytes. Let's go a little bit deeper and look at the 2 tasks. So there were 2 tasks that were required to run this job, task 0 and task 1. One of the tasks ran on this executor ID, and the other one ran on a different executor. So task 0 read about 6 megabytes of data, and there's the other task 1. So they seem to have kind of read half and half of the data. Essentially, what's going on here is the reason we had to actually execute a job, and the reason this is different from RDDs, is because it's inferring schema. And notice that right away, it actually told me what kind of data I had. Right? When you work with RDDs, when you make the first base RDD, it doesn't even go and check if the file is there. It'll give you an error much later when you call an action. So also, if you work with Parquet, the same thing happens. So this is something new and different if you come from an RDD background. OK, so now I want to do a few things. So first, I can run DataFrame.show, and it just kind of shows me all the data here. So it looks like I have a birth date, first name, gender, last name, salary, social security number. Did show run a job? Yeah, it did. It ran something, and well, notice something interesting, actually. So this only needed 1 task that read 6 megabytes of data. So what is going on here? So now you should be kind of confused. So this job, show only needed to read 6 megabytes of data with 1 task. What could be going on? It is the first 20, but the answer is actually more sophisticated than that. So what is actually going on here is up here. Remember, I kind of lied to you. When I did this, when I kind of looked at this, and then I actually just converted it over, this was kind of a trick. The actual data is not 13 megabytes. The data is actually about 6.6 megabytes, and then there's another file with schema in there. Right? So there's 2 files in my actual folder. So when I do the first read, Spark has to read that schema file and my underlying file. That schema file, well, actually, this is JSON, so there's no schema file, but it has to take multiple passes on the data. The first time it's trying to infer schema. The second time it actually makes the read happen. With Parquet, the first time, it's going to read the other file, the footer file I showed you. And then in the actual job, it'll actually read the actual Parquet data files. All right, so when I do show here, what's going on is actually it's now having to only read the JSON file once because the schema has already been inferred. So that's why we're only seeing one task with the 6.6 megabyte read. All right, so that's what we're seeing here. One task with only 6.6 megabytes of read. All right, so it doesn't have to go through it twice with another job. OK, so that's one thing. Let's do a couple more interesting things. You should always be aware of this. This is what I usually run in the very beginning, print schema to just kind of see how everything looks. It looks like it's strings, and there's a long in there as well. You can also run Markdown in these notebooks. So here's a Markdown cell. So what we're going to do now is make a new data frame that looks at just a subset of the columns in the first data frame. So I'm just going to copy and paste the code in here so you can see what this looks like. All right, so on the first data frame, I am going to select out only 4 of the many columns. And I get the name data frame. Now, if I run this, I'm going to run it actually one more time. Do you think there will be a new job that will show up? I hear a bunch of no's, and that is true. The last one is going to be the show that's showing up. OK? So this is not triggering a new job because this is a lazy operation. I'm going to have to actually call an action before it will compute this data frame. So I'm going to, on name data frame, I'm going to say show. And now instead of 5 jobs, I should get my 6th job. And this one's going to just have 1 task as well. OK?
Question?
Yes?
So it shows only giving you the first 20 rows. Why does they have to scan 6 megabytes a day?
It's a good question. I think it depends on the data format. This is a small JSON file, so it's just going through the entire thing. If this was Parquet with like 20 different data files, it would just go to the first one. Right? So that would still require just 1 task to read 1 HDFS block instead of all 20 HDFS blocks.
Basically, there's no intelligence in the JSON.
Yeah, exactly. JSON prevents it. Exactly.
So if you have a 10 GB JSON file, it will be in count?
I believe it would actually go through the entire thing. I would have to test it, but I think it would unfortunately go through the entire thing.
No, but how many partitions did you create for the SQL context?
For the SQL context, I think right now it's creating 1 partition, but we can.
That may be the reason that it reads everything because you only have 1 partition.
Yeah, that's a good point. So, OK, I'm going to actually get to that in a second. We'll play around with this in a sec. Let me just show a couple more things. You can call count, so you can see how many different rows there are. There's 100,000 rows in my data frame. OK, that's nothing cool. How about this, though? How many male versus female people are in here? So I can do a filter on name data frame and then run count. Now, before I do this filter, I want to show you something. This count here, right, on just the name data frame, which is this one, notice that, let's see what's going on inside here. So it seems to have done more stuff now. When I did count, it actually made a stage boundary, and it did a shuffle. So anytime you see a stage boundary, it's basically an all-to-all network movement. There were some maps builds here, and then there's some reducer kind of threads that started up here. OK. And it looks like this required 2 stages here. I'm sorry. And the first stage, it read some data file. And it looks like speculative execution actually kicked off, which is kind of ironic here in a small data set. And then in the second stage here, it actually does the count aggregation. OK, so let's run that one more time, because I want to point something out here. So here we have, OK, it looks like it's running 3 stages. I mean 3 tasks. If I do this, though, if I do a filter on gender and then do a count, that looks like it's half the data set. So if I refresh this, how many stages do you think will be in the job? And how many tasks? the number of stages will be the same and the number of tasks is the same, right? So what Spark is essentially doing is it's pipelining the filter into one of the earlier transformations. So if I come here and if I open this up, this is going to look exactly the same. Okay. So there's other things you can do. You can manually control the number of partitions. So I can do this. I can repartition my name data frame into 20 partitions. And then I can do maybe a filter. Let me paste the rest of this code in here. On gender and run count. This is going to take a little bit longer because I'm now running on a whole bunch of partitions. And you'll notice this actually took a little bit longer. And it ran on many more partitions. Let's actually understand what's going on a little bit deeper here. So on the first stage, it just looks like it just reads the data. It has 2 tasks. And actually, it's not just reading the data, but it's having to refigure out the schema right now as well. OK, what's the second stage doing? This is where I did a repartition. Each one of these black dots is an actual RDD. In the repartition step, there's actually a shuffle RDD, a coalesce RDD, and a map partitions RDD. Inside here, you'll notice there are actually many different tasks. There's 20 different tasks. And then it looks like there's another actual shuffle that takes place. Let's look at how many tasks are in this stage. There's actually only 1 task in the final stage that ran for 57 milliseconds. This is the stage that actually gives us the count back, all of the records. The task that gives us all the records back. Right? What I suggest doing is if you're new to RDDs, as you're writing these really simple aggregations and simple code, start immediately trying to understand what's going on behind the scenes. Because when you start writing much more complicated code, if you then start trying to decompose the stage boundaries and stuff, it becomes very complicated. So I highly recommend starting to look at the UI and kind of keep looking at what's going on behind the scenes and trying to figure out what it's really doing. In DataFrames, you can kind of cheat, and a lot of the optimizations will work for you kind of out of the box. But like I mentioned, the number of partitions is not something that it's controlled out of the box right now. So you do want to start looking at some of these settings, and this will make you just a much better Spark programmer. OK, one more thing I want to show is this. Imagine that I take my name RDD, then I repartition it to 20, and then I cache it, and I make this RDD called the data frame called cache named data frame. OK, notice, by the way, when I click on storage here, nothing shows up. Storage tab is just for cached RDDs and data frames. So if I do this, so I basically repartitioned my name data frame into 20 partitions, decide to cache it. I come back here, and it still doesn't show up. So cache is also a lazy operation. I have to actually call an action on my cached data frame before something is going to happen. So let me now do my filter and my count. OK, so now the count is actually taking place. It's actually executing everything. It's actually rereading the data and then doing my filter. First is doing my select up here to bring down to just these few columns. And then it's doing my filter. OK, now if I come to storage, I see my RDD. Actually, it is a data frame, but it decomposes down to an RDD when it gets serialized and stored. I can see that it's 20 partitions. It's 100% fit in memory. Size in memory is only 2.5 megabytes. Notice that it is more efficient than the 6.6 megabyte JSON file. If I click on this, I can see which executors each partition is on. And ooh, notice that one of the partitions is actually kind of empty. You can see how big each partition is. Oh, actually, no. This is looking at executors and how much memory is being used on each executor. This is actually looking at the 20 partitions. And notice that each partition is roughly 128 kilobytes. And it is in memory. It didn't have to go down on disk. OK, so one other thing you should know about RDD versus DataFrame storage is that in RDDs, it's actually OK if you try to cache an RDD and the entire thing doesn't fit in memory. Maybe only 10% of the RDD fits in memory and the other 90% is on disk. That is actually a healthy way of still using RDDs. With DataFrames, that unfortunately is not true. With DataFrames, you really want the entire thing to fit in memory if you're going to try to store it in memory. One of the main reasons for this is because if the data frame doesn't fit in memory, and one of the partitions, let's say, is spilled down to disk, then what you'll have to do is every time you have to go and reread that from disk, you'll have to infer the schema and read it up into memory, and that's going to cause it to serialize it as byte buffers in memory. And then once it's in memory, then to actually analyze it, you have to deserialize it as well, the byte buffers, and bring it down to something you can compute on. So if the data frame does not fully fit in memory, you might want to not actually cache it. Instead, use an efficient storage format like Parquet and just reread it every single time. That'll probably give you better performance than storing the data frame like only 20% of it in memory because of the cost of creating those byte buffers in memory and then deserializing the data out of that byte buffer. Right? I would recommend testing that yourself to see that and decide if that cost is the cost is showing up for you as well.
For
Yes.
Parquet, the schema is fixed, right? Why should it again infer the schema? For JSON, I can understand.
For JSON, it definitely does. For Parquet, I think that the point is that if for a single Spark application, it might not do that, but it might. You'll want to check that because if the format changes with every read, by default, Spark wants to go and check the schema before it actually goes and reads the data file. There's a way to turn that off.
The footer should have that.
But even the footer can change if in the background some administrator changed that data format and the programmer here kind of sat still for 20 minutes and then he tries to read it again. That original format might not be valid for that same data file. You can tell Spark you haven't messed with the schema and then it will not infer schema. So you can force it to not have to do that. But the default behavior is to actually infer schema every single time before reading the data files for the data frame. OK. So now that I actually cached this, I want to show you something. If I now go look at the DAG, I'll see something special now. I'll see this green dot. This is my cached RDD. Notice that nothing else is actually cached. Right, so this is another really just a cool way to start looking at this new UI that showed up earlier this year.
So I don't understand something. You said it's your data frame is in memory. Cache is also in memory. Nothing is written to the disk. So you have two items that are parallel to each other in memory. What's the point of that?
Say that one more time. There's the
Your cache is in memory.
yes.
The data frame itself is in memory. What?
The data frame was not originally in memory. The original data frame is actually this other data frame. Remember, it was first DF, right? We took first DF, and then we basically selected only some columns out of it, called it name DF. We never cached any first DF so far. We haven't cached name DF either. And then on name DF, what we did is, let's see, this is kind of where we started. We took name DF, then we repartitioned it, and then we cached the output of that. Right? We cached the output of that, and then on that data frame, then we did a filter and a count.
Data frame is not data. That's what I'm
The data frame is not the RDD. That is the actual point. Yeah, that's exactly it.
Yeah, that's a little bit.
That's exactly it. If you try to map the data frame to an RDD in that UI, it will not make sense. That was kind of one of the things I was trying to point out. The number of data frames we've worked on are actually what, like 2 or 3. We had the first DF, then we had the name DF, and then we had a repartition. That's 3 data frames, right? But if you come here, there's way more stuff going on. There's this RDD, then there's this map that seems to have been applied on there, then a map partitions, then we did another map partitions, and another map partitions actually. So there's a whole bunch more RDDs. By the time we got to something we cached, there were 1, 2, 3, 4, 5, 6, 7, 8 different RDDs. And we actually cached I think the 9th one. And then after this, there's 1, 2, 3, 4, there's a whole bunch of RDDs. And then we finally get some results out of this. But from our perspective, we just did a filter and then a count. All right, so yes, there's not a one-to-one correlation between a data frame and an RDD. That is definitely a major takeaway right now.
And it seems like the RDD was not very amenable for column-oriented calculations, and this one is, right?
RDDs don't do anything from a column-oriented perspective. Yeah. With the RDD, you're going to have to, if you want to do anything with an RDD, you're going to have to go through every single item.
Right. And the data frame, you have that abstraction, right? You can work.
That's exactly true. If I had more time, I would have contrived up a demo where, maybe if you can throw all the female people in just certain partitions, and then have a cache at that. RDD, then you would have noticed that the calculation would have been much faster because it would have looked at just 50% of the partitions.
So are there libraries being built around the data frame? Because that's the next question.
Are there libraries being built around the data frame? See, that's a tricky question because you're literally standing on the line of RDD world versus data frame world. I think that in the future, there's going to be a lot of different libraries built on data frames directly. Even right now, though, if you look at this slide, right now, Spark SQL is a higher level library built on data frames. MLlib already is working with data frames right now. Spark streaming does not work with data frames, and GraphX does not work with data frames right now.
So the existing functions in MLlib, like the TF-IDF transformer?
I believe that one just works with data frames out of the box. Okay. So the question is now, what do you do with Spark streaming? You're going to have to convert the D stream into an RDD first, and then convert that with schema into a data frame before you can work on it. But in the near future, I don't want to give a time frame, but probably in the next 6 months, data frames will work out of the box with Spark streaming, and you'll be able to take a data frame and give that to the GraphX library to get actual nodes and vertices out of it as well. So all of the Spark high-level libraries will work with data frames out of the box by the time Spark gets to probably Spark 2.0. But I hope that most new people who make libraries, it depends on what the library is doing. If the library is working with structured data, it should definitely be built on data frames. If it's doing something with unstructured data, like facial recognition, then it needs to be built on the RDD API right now. Right? That's basically the easy divide between figuring out which one you'll use. OK. I want to finish up my demo because I do want to talk a little bit about the Catalyst engine, and I think that will be something useful for people who have not kind of even been using data frames for a long time. So what I'm going to do is I'm just going to put up a little bit more code here to just show you a couple more things, and then I'll talk about Catalyst. I want to show you how schema inference works. So imagine that we have some text file, people.txt. This is what the text file looks like. Let me make that a little bit bigger. All right, so this is your traditional RDD API. We make an RDD out of Spark context using the text file method, and this is each line is just a bunch of delimited strings, it looks like. So on this RDD, we can take 10, and then we can print each one of those, and that's what we're seeing. So how do we convert this into a data frame? We can see there's clearly structure here. It's just Spark can't figure this out automatically. So you can see that's first name, middle name, last name, gender, birth date, and then salary. That's the salary column, and then social security number. So here's the code essentially for how you do this. You're going to have to create a case class. Here we make one called person, and we put what our schema looks like in there. And then on the RDD, we use map to go through each line, and for every line, we split it based on the delimiter. We get the column, and we apply the case class. And notice we did something a little bit fancy for birth year. Since the format was like that, we figured out how to explode that into an actual time-oriented format. And then what we do is on this people, this is a lazy thing because remember map is a transformation, so this never got applied. So to actually apply it, we say people RDD dot to DF, and then we get a data frame. It's really as simple as that. Once we get a data frame, then we can start operating on it like a data frame. So I can do a show, and now you're basically just in like data frame world. There we go. There's the schema. And you can also sample data in a data frame. So here I'm sampling just like 2% of the data.
So could I also
Right.
interpose a data frame in the middle of my Spark code where I have dealt with RDDs and then I have a massaged kind of reduced RDD, which is very small, and I just bolt on some column names and boom, it becomes a DF?
Yes, you get the DF, and then
Do that? Okay.
yes, that's exactly the point.
Because I don't want to start out with that.
Yeah, that's exactly the point. So here's another thing. What if you want to run SQL on your data frame? So I'm going to register my table, my data. So there's my data frame. On this, I register a table called people. And then you can just basically start running SQL queries. So here I'm just running a SQL query to look at people born in the 1970s. And I'm ordering by birth year and salary.
Couldn't you do that with the filter?
You could do this with the filter, and I think I have an example of that somewhere. Let me see if I can find it. Here's the same thing in data frame world. I think it's something. This is maybe not the exact same thing, but yes, you could do something similar to that. So a lot of things you can do in SQL or data frames. That one specific thing is one of those. Oh, here we go. So this is the same thing in data frame code.
Which code is more optimum?
The exact same. So when I talk about Catalyst, which I'm going to switch to in just a second, you'll see that this code, which is giving us, look at these results, basically looking at, we're filtering out people who were born in the 1970s, and then ordering by birth date, and then salary. All right, that's the same thing as what we did in the SQL query, actually. So let me scroll up a little faster. And if you look at the results, it'll be the exact same right here. So what is the benefit of either or? It really doesn't matter. Both of these things are going to go into the Catalyst optimizer, and the same physical plan will come out. There's literally no cost difference. So let me start talking about that next. Let me see if there's actually anything interesting else to mention here.
The temp table is only valid for this session.
The temp table is only valid for this session. If you want to have a permanent storage of this, you're going to have to most likely either save it as a permanent table and register the schema in Hive's metastore, or better yet, store it as Parquet in HDFS. That is exactly correct. OK, so let me talk a little bit about Catalyst. And this is kind of where it will get a little bit more technical. But I hope that this is going to be useful for people who have already been using Spark for a little while.
So I have a question.
Yes.
Imagine if I have a matrix where the number of columns is 15,000, but because they are sparse, I have implemented them with a sparse vector, but it's in the form of an RDD. So can your data frame have this concept of a sparse vector being the set of?
Yeah, that's a good question. I'm not sure. Because you have types there. I don't know if you have names on those columns. If it's just a vector, I don't think it's named.
Well,
So
I do have a reference to what I call feature names, which are
Okay.
basically references.
Okay, so that should convert into a data frame then. And then once you convert it to a data frame, these optimizations I mentioned, like the statistics, should still apply.
So you mean the sparse vector will become a dense vector, and I would need to, and it will become huge. I don't know if this will be able to handle it.
That's a good question. I haven't done that, so I'm not sure how that would actually translate down. Yeah.
If you use a columnar format, it might not matter because the whole idea is to optimize every column. Some of the column values are sparse, that's what you have. Like
You have zero.
they're loading nothing.
Yeah.
So it will be compressed. So something to look at, like maybe
Just make
Yeah.
a new value for the column.
Okay, so let me talk a little bit about what goes on under the covers in DataFrames. So this was maybe our SQL query that we wrote, or maybe our DataFrame query. You kind of saw that both of those go into Catalyst, and what essentially is going to come out eventually is a physical plan. So I'm going to spend like 10 minutes talking about kind of like the cloud part in the middle. But notice that what we're trying to get to is ultimately just a physical plan that we can run, and that's kind of what we were looking at. When we looked at the DAG visualization, right? What we were getting is actually the run of the physical plan, which was under the covers using many different RDDs. Okay, so remember, what we're trying to do is basically take our data frame operations and get the physical plan that's most optimal, so we can then run it like any other thing runs in Spark Core, which is like the entire directed acyclical graph. Okay, so at the high level, there's two types of optimizations in Catalyst. There's logical optimizations, and there's then the physical plan generation in JVM bytecode. So here are some of the logical optimizations. For example, pushing filter predicates down to the data source so that irrelevant data can be skipped. We talked about this in many senses. We talked about that with Parquet and also with partitions in Parquet. So with Parquet, for example, you can skip entire blocks. Also, what you can do in logical optimizations is turn comparisons on strings into cheaper integer comparisons via dictionary encoding. On a relational database, maybe what you'll do in the logical optimization phase is simply push a predicate down to the relational database so you only get certain rows back. And then finally, the next phase of optimizations is the physical plan and generating bytecode. Here, Catalyst can optimize operations into a physical plan. And it can, the only thing that it actually does as far as choosing different physical plans right now is it can either choose to do a broadcast join or a traditional shuffle join. So in Spark right now, the threshold is set to 10 megabytes. If you're trying to do a join between two different data sources, and if one of the data sources is less than 10 megabytes, then it's going to broadcast that 10 megabytes out to every single executor, and then it will basically take that small 10 megabyte data set and then join it with perhaps a partition of a much larger RDD or a much larger data frame. In the future, there's going to be a lot more intelligent choices that will be made. So what I'm trying to show you is right here. If you have multiple physical plans, let's say one of them does a broadcast join, the other one does a more traditional type of join, then we can choose between the two. And like I said, right now, that's the only choice that's being made. But in the future, there should be a lot more interesting choices that will be made or in that phase. OK, this is something you might have already seen. Anything that you run in DataFrames runs at native bytecode level in the executor JVM. So the performance you get with DataFrames is independent of the language you're creating the data frame in. Versus if you use Python and PySpark with the PySpark API, then any UDF you write in Python runs actually not inside the executor JVM, but in a tiny little Python PID next to the executor JVM, which is why Python is sometimes 2 to 10 times slower than Scala or Java RDD code that runs in executor JVMs. But that problem doesn't exist as long as you're using DataFrames. OK, So I'm going to kind of start unwrapping a little bit more behind the scenes with DataFrames. So the two high-level goals of Catalyst was to first make it easy to add new optimizations without having to go and mess with the earlier optimizations that were written. I'll show you some of those optimizations. And then finally, it was written to be very easy for developers to extend the optimizer to add either new rules or to add new data types and new data sources. Okay, so the first thing to understand about Catalyst is something called trees, and trees are just an object. This is the main data type in Catalyst. Everything translates down into this data type called trees, this object. Trees are made of node objects, and each node has a type and 0 or more children. Let's just kind of draw this out. Imagine we have the following 3 node classes for a very simple expression language. So we can have a literal, which is a constant. We can have an attribute, like a name. And then we can have this operation like add, which takes the tree from the tree node and another tree node and gives you the sum. So imagine that we need to build an expression, build a tree for this expression. How would this look? In the Scala code, the expression would look like this. We want to add attribute x to, actually I have a messed up parentheses here. We'd want to do this first. So add these two. And then the output of, so we add the 2 literals. And then whatever we get from that, we add to the original x. All right, so keep this in mind, because this is like the original, the fundamental data structure in Catalyst. These nodes are immutable. So if you have a object like this and you want to convert it to another object, you'll literally have to transform it. This is like the functional programming paradigm, right?
That's correct, right? What you wrote?
What's that?
Add literal.
Yeah, this is slightly incorrect. I should actually put another parentheses basically there.
No, I think so. No, you have to add the
Did I do that correctly?
parentheses.
Oh, okay, yeah, that's right. That is fine. I misread that. Okay, so we have our fundamental data structure, the tree, right? It's just a Scala object. So next, what we need to do is we need to apply rules on our tree, and here are some of the rules. So trees are manipulated using these rules. Let's implement a rule to do that follows the add operation between constants. So here is a simple rule that we created to actually do the addition. So let's try to apply this rule to this tree. What would we get out of this? Well, the yield would be essentially this. You'd fold these 2 operations, these 2 constants into one constant once this rule gets applied once to this. Okay, so a few more tricks about this. The rule may only match a subset of all the possible input trees. So imagine your tree being really large with like hundreds of different nodes on it. And when this rule is being applied, it's going to start crawling down the tree, and it might apply to a subset of the tree, and then you get a new tree out of that. Then it kind of keeps running, and it might apply to another subset of the tree. And you're going to basically keep applying this rule multiple times and keep getting new trees out of this. And there's many, many different rules. Sometimes a rule can do multiple things. So this rule is very simple. It's only looking for add nodes, then getting the 2 childs from the add node, and then giving you a new node out of it. So the resulting tree would be 3 nodes. And then this gets, perhaps if you had another rule that knew how to work with x and a constant, then we would perhaps have gotten another tree out of that. So let's make a slightly more complicated rule. So this rule now can actually match multiple patterns in the same call. If you look at what it's doing, we have not just the add, but we're also getting rid of basically anytime we're doing an addition to just a 0, we get rid of the 0. So notice here when we applied it to the original tree, we get the exact same thing. But on this tree, we also prune out the 0. So with one call of the rule, we get rid of the 0, and we do the addition. OK, so let's build a little bit deeper into this. This is a recap. Rules may sometimes need to be executed multiple times to fully transform the tree. And rules are grouped into batches. And each batch is executed to a fixed point until the tree stops changing. So here are some examples of this. Maybe you use a constant to fold larger trees. Or maybe you apply the first batch to analyze expression to assign types to all attributes. So this is where you're just typing all the things. And then finally, you're actually doing constant folding. OK, so this is the first thing in Catalyst. We need to basically create the trees. And then we need to do the analysis phase. The analysis phase is basically not just making the logical plan, but also then looking at the catalog. The catalog is going to be something like Parquet or Hive, and it's getting things like the data types and applying it to our tree in Catalyst. So I think I have a slide on that. Yes, the next slide will cover analysis in a little bit more depth. Just remember that the phases here are we have to take the unresolved logical plan, apply information from our meta store of Hive or Parquet to get a more optimized logical plan. And then we're going to optimize that even further in this logical optimization phase. Then we do the physical planning phase, which will get us the perfect physical plan. And then finally, we're going to run the DAG. This is where you see like the graph in the UI. Okay, so I'm going to just give you one slide on each one of these operations so you can kind of get a little bit of understanding of what's going on behind the scenes. So either we have a SQL AST, that stands for Abstract Syntax Tree. This is like our tree that I was mentioning. Or we have a data frame. And both of those go into an unresolved logical plan. We then apply data types and get the logical plan, the initial logical plan. OK. Next, I'm just going to go through this really fast. What we're doing in the analysis phase is essentially applying rules. And there are many rules, and with every new version of Spark, new rules are being added. This is why Spark out of the box just becomes faster with more optimized rules that just come in new versions of Spark. So I'll let you kind Does the order of rules matter? Is that what you're asking? You don't have any say on that. Spark itself will decide which rules to apply in which order. Does that answer your question?
Because starting the SQL rules were customizable.
In Spark SQL?
Yeah.
You can create new rules, and you can influence your tree evolution with your rule as well. But I don't think you can force your rule to run in a certain order. That might be different, but I'm not 100% sure about that. But I don't think you can control that. You might be able to. I haven't done that myself. Were you able to do that in schema RDDs? Yeah, I don't know if you were able to influence the order time run of the rules. I think the Catalyst engine will decide the ordering of the rules itself. All right, so essentially that's all we're doing right now. We're essentially just applying rules. This entire analysis phase is 500 lines of code, and it's called analyzer.scala. That is the actual object. That's the class that creates the analyzer object. So this is my point to show you this is actually that this is actually very, very hackable and readable. If you want to actually hack Catalyst to do something very unique, well, the analysis phase is only 500 lines of code. You'll see this next phase is actually, I think it's less, this next phase is 700 lines of code. So here we're basically taking the logical plan and running even more rules on this. So here we're doing constant folding, predicate pushdown, object pruning, null propagation, and a whole bunch of other things. For example, here's a 12-line rule that converts like expressions in SQL into simple regular expressions with string start with and string contains. Right, the main thing actually here was we were assigning types and matching the data to the data in the abstract sense to the actual underlying data. And here's where the bulk of the rules are actually being applied. And this is an optimizer class, optimizer.scala, 700 lines of code. And then finally, the physical planning stage. This stage is going to be probably evolved a lot in future versions of Spark, but what's happening here is basically we take the logical plan and then we create some physical plans, and the only transformations that Spark uses are these three, and it makes some physical plans. Right now, the only cost-based thinking it's doing is, should I use a broadcast join or a traditional join? Remember, the threshold here is 10 megabytes. If one of the data sets is less than, and you can tweak this. There's a setting where you can make it 20 or 30 megabytes if you want, if that is something, if your JVM, your executive JVM can handle that, that is something you might want to do. OK, so we then pick a physical plan. This is 400 lines of code. Spark strategies.scala is the actual class that gets instantiated. And then finally, we need to make bytecode to run. Remember that we get our physical plan, and then regardless of whether we're running in Python or R or Java or Scala, we get the same bytecode that runs in the executor. And that is the code generation phase, which is about 700 lines of code. So here we're taking the physical plan and then actually making the runtime bytecode for that. So here is, for example, some code gen that converts an expression like this to a Scala AST. This is using something called quasi-quotes in Scala. You can almost think of this phase almost like a compiler. It's just compiling the physical plan into optimized bytecode. And in Scala, the way you do this without like having to rewrite a compiler from scratch is quasi-quotes. All right. I have, I think, a few more slides, and that's, so if you care more about this stuff behind the scenes, and if you really do want to start hacking and making more rules for a catalyst, then there is a blog post on the Databricks website. It's very readable. I would highly recommend reading that, or you can read the Spark SQL paper, which was only released, I think, like 2 months ago. So this is a very, very, very new project. The entire project is like 1.5 years old, and it's going through like this very, very major kind of like move right now with Project Tungsten and with new stuff happening with Catalyst right now. OK, the last thing I wanted to mention is basically UDFs are also very easily done in Spark SQL. If you've been using like Hive, then UDFs are something that are kind of tricky to use. I mean, they can still be done, but not quite as easily as in Spark. So you don't have to like register UDFs or do anything like that. You just basically make your UDF. Here we're basically taking in a zip code, and there's some custom logic to return the city of that zip code. And to actually use the UDF, all we're going to do is on the events table, we're first doing a join between the users table. Between the users table and the events table, we do a join, and then on this column, we're basically converting zip code to city, and then we get a new city column. How do we actually use this in real code? So here is something kind of interesting. So here's the UDF we create. Here's the function actually that we created, add demographics, which is actually reading data from SQL and then doing a join and then actually applying our UDF as well. Then we get events. And then on events, we are looking for city San Francisco that meets a certain timestamp. Then we do a collect, and we get our training data. So the logical plan would look something like this. So we have our original data, the users table, and then the events file as well. And then we do the join here. And then we're doing a filter later on, like way down here. So this is our actual logical plan. So what will Catalyst do with this? Well, this join is expensive because we're reading all of our users table and all of our events table. So what Catalyst will do is it's going to figure out that actually we can scan the entire users table and then do a filter. So it's pushing the filter under the join, even though your user code didn't do that. And then it's reading all of the data from our events table as well, which is doing a full scan on this. So maybe our events table is something like right now coming out of JSON. There's no further optimization we can do. It's not like Parquet. However, with maybe this source is coming out of Hive, so we can actually do predicate pushdown, or we can do partition optimization here. All right. So now imagine taking this to the next level. Like, to actually make this production ready, what I would recommend doing is actually having a partition table in Hive, but also convert the events data instead of JSON to Parquet. If you do that, then even the events table will be optimized and will only read the columns that we care about. And then the filter will also be optimized with the Hive table. And we will use partitioning to also look at only just the folders that we care about. So it's not, with Hive, it's going to be doing folder pruning to look at just the partitions it cares about. Then within that folder, it will be more optimally looking for just the columns as well. So it's doing like a two-level optimization versus with Parquet, perhaps it's not able to do that. Unless you have, you can do that really for Parquet as well. You can have partitioning and then column pruning as well. All right, so the point here basically is that if you use RDDs and you tell Spark what you want done, it will do it exactly how you told it to do it. It cannot add intelligent optimizations. Out of the box, Catalyst will start adding optimizations like this, but these are usually not sufficient. To really go to production, you will need to use best practices like not JSON, but Parquet, and not just normal Hive, but actually partitioned Hive tables to actually get the full power of using Spark in production. OK, I have, I think, 2 more slides, and then we're done. Another thing with Spark is that Spark 1.5 is actually a really major release because Project Tungsten comes in Spark 1.5. This is a really massive project. I won't say much about it except to say that Project Tungsten is basically a reimagining of the core engine in Spark. So this is like a revolutionary change to Spark core engine. And most likely, whenever Project Tungsten is finished being implemented, like maybe around Spark 1.6 or 1.7, we will probably make a new major revision of Spark to Spark 2.0. This is that major of a thing. So you can see here that when we are looking at something like, I guess what were we doing here? I think this was some sort of operation that basically caused essentially the heap on the GC to go kind of crazy. So garbage collection time is going nuts here, default. With CodeGen, it gets a little bit better with garbage collection time in seconds. But when you go Tungsten on heap, it's a lot better. Tungsten off heap is much better. One of the things that Tungsten can do is instead of caching the RDD or the data frame inside the executor, it will cache it off heap completely. So you're not triggering garbage collection as often in the heap of the executor. And then also there's much better serialization costs with Tungsten. So even if you're using RDDs or not using RDDs, like if you're using DataFrames, when you go to Project Tungsten, it's always manually managing the memory off heap. So you don't have GC pauses. This is one of the main things you get rid of with Tungsten. OK, finally, one last thing you get in Spark 1.5 is I think it's like 150 new functions. So if you've used DataFrames right now, probably in about 3 days, you can figure out in Spark 1.4 everything there is to do with DataFrames. The number of functions is actually quite limited. In Spark 1.5, that changes. There's like 150 new functions that you get that are optimized with CodeGen implementations. So, and then finally, another thing that is new in Spark is window functions. I'm not going to cover this much other than to say that In general, before Spark 1.4, there were just two types of functions that you could do in Spark SQL. They were basically built-in functions or UDFs. What these would do is a single row would go into the function, and then a single return value would come out. The other thing that you could do before Spark 1.4 is aggregate function. So a group of rows would go in, and a single value would come out. Right? That's all you could do before. But with window functions, you can do things like moving averages and cumulative functions. The idea now is that you can operate on a group of rows and still return a single value like before. But what you're doing now is basically you are looking at the group of rows, and instead of just doing the simple operation as before, you can keep track of essentially that item as you're moving through the different rows. Okay, this is an actual really good blog post of explaining how this works. Has anybody here used window functions? 2 or 3 people? Okay. A few people. In SQL, yes, but in Spark SQL, I think it's very new. I think it's like a couple of months old, I believe, or a few months old. Okay, and this is the very last thing that is like a cutting-edge new feature that we haven't really talked about publicly at all yet. This is probably like the first talk that's even mentioning this. DataFrames functionality is coming to be as a built-in functionality in Spark Streaming. You can start looking at this umbrella JIRA, which will very soon start having sub-JIRAs on it about the actual work being done. This is like really cutting edge. This is only in a design phase right now, so we don't have any sub-JIRAs under this. But in the next 2 or 3 months, you'll start seeing a lot of the implementation of how this will be coming in the future in Spark Streaming.